All right, welcome everyone to our webinar for the Reproducibility Challenge. So, again, I'm Jeanette. I'm the chair of the competition, and I'll introduce Julian here from UC Denver. So take it away, Julian.
Yeah, thank you. So there are three of us on the call. I am Julien, and there is Lionel Hérault-Dubois from INRIA, and Mathieu Vérité from INRIA. INRIA is a research institute in France. And so last year, Mathieu, Lionel, and I got a paper submitted and accepted at SC. And we are very excited to be part of the Reproducibility Challenge. And so we want to welcome all the students. And we're here to answer the questions. So either through Discord or as you want. There is really 5 of us. So this is Lionel, Mathieu Vérité, Mathieu Faverge, and Florent Prouvost, who are helping out with the Reproducibility Challenge. As far as SC, the conference itself, I think I'll be the only one. Actually, I am in Denver right now. And I think, I'm not sure you can see from the window, but the convention center is right there. So I'm a block away from the convention center. And that's it. So I'll be excited to see all the students and everyone during the conference. As far as the presentation goes, most of the talking will be done by Lionel. So maybe Mathieu wants to say hi, and then we leave the floor to Lionel. Mathieu, you want to say hi to everybody?
Yeah, just already talked a few minutes. So hi everyone. I was part of this paper that we did with Lionel and Julien last year, and so it's nice that it has been selected for the challenge. Maybe I will let the floor to Lionel so that he can explain what it consists in.
Okay, so if you can hear me correctly, I will share my screen. No, I cannot share my screen, so I will wait for Janet to allow me. In the meantime,
Yeah.
so
let me fix that. Okay. Yeah.
Yes.
Yeah. Let's see. Do I have to like make you host or something? Let's see what I can do here. Yes, I will make you a host.
Okay. So I'll try to share my screen.
Yes.
Hopefully it works. Okay, I can find this guy. Yes.
There you go. Great. Yes, we can see that. Great.
So,
well, wait a minute. What did it do?
Does this work?
No, it's shrunk it for some reason into a little corner.
So
oh my!
Let me cancel it. Okay, is it better like this?
No,
it's really bad.
Yeah, it's just showing like
no,
the
not.
upper corner of your. There you go.
It's better like this, right?
That's good.
It's good like this.
Yes.
Okay,
fine.
so it means I won't be able to see you, but never mind. Okay, maybe hold on 2 seconds. This I'll move here. All right, is it okay for you?
No.
No.
Again, we just see that corner.
Okay. All right. So, okay, fine. This is good, right?
So
yeah, but then it goes to the corner. It's there for a minute, but then I think you try to switch back.
Just don't go full screen, maybe, Lionel.
I'm not going full screen, but I'm trying. Hold on.
And Mathieu and I will monitor the chat if you need. We can monitor the chat for you.
Okay.
I'll be watching it too. All right.
Oh God.
How good is it?
It's bad.
Sorry about this.
Bad.
Not sure what's going on. Okay. Let me change something. Perfect.
That's good.
Yes, I just need to find the correct sites. Yeah, this is good, but it's not the right file. Hold on. good is it?
Good.
Perfect.
Nice. Okay. So this is, so excuse me for the technical problems. I will start by giving the like part of the talk that I gave to SC to present the paper that we presented there. What are the results that we got and how we got them and what it means and what's the context of this work. And then I will switch to some other set of slides where I will explain to you in more precise detail what we expect of you for the particular reproducibility challenge. So this symmetric block cyclic paper was presented at SC last year. Is a joint work with Lionel, Julien, and Mathieu, who you know from in the talk, and two other people, Olivier and Philippe from Bordeaux as well. So the context is what we're doing is data placement solutions for linear algebra. So you probably know linear algebra in scientific computing is like a cornerstone. Every time you want to solve partial differential equations, you end up with solving a linear system after you discretize. And it's something that you want to do in the distributed way because there's a lot of work to be done. And so it's important to minimize the communications because this is something that limits the performance of the applications. And so the context in which we're working is that we look at one specific operation that is done in linear algebra, and we don't change the algorithm, we don't change the computations that are being done. What we will change is how they are organized how they are distributed over the nodes, with the goal of reducing the total volume of communications. And so it's something that has been looked at a lot in the past, but what has not been looked very specifically is what is the effect, or what it means, what changes when we look at symmetric operations. And symmetric operations, the most well-known one is the Cholesky factorization, where you factorize a symmetric matrix, and it happens a lot because many physical problems have symmetric matrices when you discretize them. And so in this work, we have proposed a symmetric block cyclic distributions, which we show improves in terms of communication and also in terms of running time performance over the standard 2D block cyclic distribution. So the 2D block cyclic distribution is a standard thing which is in ScalaPack. So ScalaPack is a well-known software, very, very old and well-maintained software to do distributed linear algebra. And the bet of ScalaPack was, okay, let's take all the linear algebra operations algorithms that we have, which were in LAPACK, and let's distribute them with the 2D block cyclic distribution, and everything will scale, and it will be great. So indeed, everything scales, but for some operations, and typically for Cholesky, 2D block cyclic is not the optimal way of doing it. It does work, but we can do better, and this is what we do in this talk. So I will start with simple considerations like how do we count communications, because this is what we will minimize, and how do we count the communication that an algorithm does. So we start with the general matrix multiplication. So we have two matrices. So for simplicity, I will assume C is square. It's not the case in general matrix multiplication, but it simplifies everything. And since we will do symmetric stuff afterwards, matrices will always be square after. So you have two matrices A and B, and also matrix C, and we want to multiply A, the product A times B, the matrix product, and store the result in the matrix C. So you can see here the well-known cubic algorithms to do this with 3 for loops to compute the product of A times B and store them in C. All right, and so when we do this in a distributed way, so the standard, so there's a lot of things I want to tell here. We do this with in all our work. We do this within a runtime system, which automatically builds the dependency graph from the sequential code. So the code that I write here, this is a sequential code where the code you would write if you had only one node, but you can easily deduce the dependencies from that and be able to identify possible parallel executions, and the runtime system can do this in parallel if you tell him where to run each operation. And this is what we will do. We give a specific distribution. The runtime system does not invent it. We give it to the runtime system. I think that this particular tile of the matrix will be on this particular node. And once you have this data distribution, there's a rule that says the owner of the tile does the computation. So the owner of this tile of C does the product of this tile of A and this tile of A to compute this tile of C. So this owner computes. And once those two rules, those simple rules are given, then it's easy, I mean, it's feasible for the runtime system to automatically handle the dependencies and automatically handle the communications. So we will not, the work we do here, we don't change the code, the sequential code, we don't change the algorithm. We only change which data is allocated to which node in order to minimize the required communications. So the standard distribution is 2D block cyclic. So for example, here I have 8 nodes. I decide to put them in a 2x4 rectangle, P by Q, and then I replicate this rectangle all over the big C matrix. And each time a style is colored with one particular color, for example, this dark green here, this is one node of my 8 nodes in my platform, and I will store all the dark green tiles on this particular node. Right, so this gives me which tile is where, and then we can guess, or we can deduce what communications will be implied by this. So when I want to compute on this particular tile of C, then I will require these tiles of A and these tiles of B. Okay, the tiles in the same column for B, in the same row for A. All right, and then this means that reciprocally, this tile of A will be used for all of those tiles of C, and this tile of B will be used for all of those tiles of C, the column of C and a row of C. All right, and then I can say, okay, each tile of A is used by Q nodes because I have Q nodes on this row. On every row on the matrix C, I have Q nodes because I have Q nodes on the row on the 2D block cyclic thing, and I have P nodes on this particular row, column in the matrix, right? And now maybe this tile of A used by the Q nodes here, maybe it's already stored in one of those Q nodes, but at least I will have to send it to Q-1 nodes. So each tile of A will need to be sent. So I have mn tiles in A, right? M times n, this is the size of A. Each tile of A will need to be sent to at least Q-1 nodes. Maybe Q if some of them are not okay. And similarly, each tile of B will need to be sent to P-1 nodes. And I need to send because I need to send both A and B. And I have a communication volume which is Mn, so size of A times P plus Q-2. Right? And this is like it's not really dependent on the ordering in which I do the computations or anything. It's just given by the data distribution of my computations, right? So there is some discussion about arithmetic density. I don't want to delve into it. I just need to say that okay, this particular communication volume for GEM is optimal. So 2D block cyclic, you cannot do fewer communications than this. Distributed when you have P nodes, you cannot do anything better. So cool, that's fine, and that's why 2D block cyclic was chosen actually in the beginning for ScalaPy. Cool, nice. And now let's do something symmetric. So the simplest symmetric things you can do is the same product, but this time B is actually A transpose. So it's not A times B, it's A times A transpose. And so it's still a multiplication, but it's particular one. So it's called circ for symmetric rank update. That's the LAPACK name of this operation. And it's actually a dominant part of the Cholesky factorizations that we are interested in. So we look at circ because it's important for Cholesky factorization. And so, of course, the result is symmetric, so you don't compute all of it. You compute only half of it because the other half is the same values. And so what happens in Scalapack and in a standard way is, okay, you take the 2D Block-Cyclic distribution and you distribute to half of the matrix following this thing, as if it was a general matrix, but you truncate one half of the tiles, and you get something like this. Right, this is what happens. And we can do the same as before. So now, if you want to compute this particular light orange tile here, to compute this tile, you will need those tiles of A and those tiles of A transpose. Of course, A transpose, you do not actually materialize it because it's the same as A. So you actually need these tiles of A and these tiles of A because they are in A transpose. Sure. So fine. And so let's do just as before symmetrically. Each tile of A is used by the Q nodes in this row of C, right? This tile will need to be sent to all of the tiles in the row here. And also, and this tile, tile, blue tile also, it will need to be sent to all of those tiles as a tile of A, and it will also need to be sent to all the processor in the column, because there's also a tile of A transpose, right? It's the same data, but it needs to be sent in the row as a tile of A, and in a column as a tile of A transpose, right? So it gives an L-shaped thing like this. And so we can say that each tile of A is used by, and if you can count how many nodes there are here, there are P nodes here and Q nodes, Q nodes here and P nodes there, and then one which is in common, which is the light green one is common in the row and the column, so that P plus Q minus 1. And the total volume, again, maybe the tile of A is within those P plus Q minus 1 nodes. The total volume is the same as before, Mn times P plus Q minus 2. So that's actually a bad thing because we are doing half the computation as before, but we're doing the same amount of communications. So in terms of arithmetic intensity, is worse. And there exists an upper bound from the SPA paper of the couple of years ago, where we show that actually we could do better in terms of arithmetic intensity. So we could do fewer, maybe twice fewer communications than this. We don't know, the gap is not closed between this upper bound and this thing. So it's not the best. We could do better, and so this is why we came up with this symmetric block cyclic distribution. And the goal, as you see, the problem is that okay, you send this tile to nodes on the row and to some nodes on the columns, and it's not the same nodes, so you end up summing them. But you would like to have the same nodes on all the rows and all the columns to get something better. So let's do a 2D block cyclic thing. So again, we have a pattern here that will replicate on the matrix just like before, but this time we're doing a square pattern. And let's replicate the nodes. Let's arrange the node however we want. For example, like this in the lower diagonal part of the pattern. And let's make a symmetric pattern, right? So you take this node and you symmetrize over with respect to the diagonal and put them here. So now we have a symmetric pattern. And we add two more nodes, which we duplicate twice to fill in the diagonal. So this thing is a symmetric pattern. It's like we can use it just like we used the 2D block cyclic pattern before. The difference is that now each node appears twice in 2D block cyclic. Each node appears exactly once in the pattern. Now each node appears exactly twice. Okay, cool. We can do this. So we can replicate it on matrix C. And let's assume we still want to do symmetric concave update. So A times A transpose. We have this pattern replicated everywhere. And now this tile of A is needed by all the tiles in this row and in this column, just as before. But this time, in the column, we're meeting exactly the same nodes as we have meeting in the row. That's the goal of the symmetric block cyclic distribution. And so we can count. We are meeting. So this tile of A is needed by R nodes, right? Because you have R nodes on a row or on a column, and we have the same nodes. And so maybe it's already in one of them. So it will be mn times r minus 1. And if we count in terms of arithmetic intensity, we get a square root of 2 improvement compared to before. So because r is square root of 2p, I don't know if I have something here, not yet. In terms of order of magnitude, r is of the order of square root of 2p, whereas if you do 2 to the Debug cyclic before, if you do a square to the Debug cyclic, p and q are the order of square root of p, and you have 2 square root of p here. And here you have square root of 2 times square root of p. So you have a factor square root of 2 improvement in terms of communications. So this is the benefit of symmetric block cyclic. So we have, there's another way of doing, so this, what I show you here is a basic version of symmetric block cyclic. There's an extended version to overcome the 2 limitations of this version, which is it needs R to be an even number, otherwise we cannot do what I did. And on the diagonal, you always have the same nodes. You see it has 7, 8, 7, 8, 7, always on the diagonal, you see always the same nodes, and that might be problematic for some cases. So we did the extended version, where you start the same way. You create a generic pattern with the diagonal not filled, and we create several patterns one after the other. So you take those nodes 1, 2, 3, 6, and 1, 2, 3, 10 moves them to the left, 7 moves it to the bottom, and you get this pattern here. Right? This is symmetric, but now this pattern here is good, but it's not balanced. Like node 3 has more tiles than node 5, for example, so it's not balanced. So we need to balance it, and for this we will make another one. So we take 259, move it here, take 48, move it there, and now we have 2 patterns, and we can alternate between them on the matrix. Instead of duplicating just one everywhere, we duplicate 2, and those are balanced because each node appears once on the diagonal in all those patterns. So we have, that's fine. And so it's the number of patterns depend if R is odd or even. So all the details are in the paper, but this is a way to solve the problem that we don't have values. We need specific values of R for it to work, and most importantly, have a good variety of nodes on the diagonal of the matrix. That's important. All right. So now we're doing Cholesky factorization. So it's I don't know if you know or not about this. So the goal is to solve to take any symmetric positive definite matrix A and write it as the product of a lower triangular L and its transpose L transpose. So we have A and we look for L, and the way we do it is it's just mainly doing the circle operation several times in a row. So if this is a tile decomposition of our matrix A that we want to have, we start by factorizing the first diagonal block here, and we update what's going on here. Of course, it's the same, and we update what's going on here, and then we need to compute this column here blue at A, as you see it was A, so let's say call it X, I don't know, X times X transpose. And this is how we update the rest of the matrix to come up with to account for the factorization that was done in the first diagonal block. And we do a large sort operation here, which we can divide actually into gems operation here and circ operation in the diagonal, which is what is written here. And then we keep going. So now that these parts are done, it's finished, we can keep going. So we factorize this, update that, and then update the rest with another circ operation. So we have successive circ operation where we factorize the panel and update the trailing matrix with a circ. And a typical MPI-based implementation of Cholesky synchronized between all the iterations. So we have this operation with big circ thing, and then we wait until everything is done and start doing the next operation, next factorization of the panel, update, wait, synchronize everything, factorize, update, synchronize, and so on. But if you look at the dependency graph of this thing, it's actually a 3D graph. So let's turn it around like this, and the dependency graph looks like this. You can compute this update on this tile at the first iteration. It requires this node, this data, and this data. and then you can do the next one, and then you can do the next one. But it's not impossible to start factorizing this panel before you're done updating for the previous iteration. And for example, this would be a possible state of the data in the middle of the execution if you have a large look ahead. And as I told you at the beginning, task-based runtime systems, you can allow for large look aheads because they just how can I say it? They just identify how much like what the task graph is, and they just do the operation in whichever order is valid, it's compatible with the dependencies. And so it's possible to like this. So you have to, you're not done updating the first iteration, but you can start the second, and you can even start the third operation before you're done with that. And so with task-based systems, so as I told you, we have more parallelism because we don't have to synchronize between iterations, and communications are managed automatically. So it's not difficult to change the data allocation because you change the data allocation and automatically the runtime system figures out which node needs to send data to which other node. So we use this in our experimental results. So we have Intel Xeon Skylake nodes in our experimental platform in Bordeaux with 42 nodes and 36 core nodes. And we use the Chameleon library so the runtime system is StarPU, and Chameleon is a library built on top of StarPU to do linear algebra. I will give more detail about Chameleon later. And so each task is executed on one core, but one StarPU process per node, which handles all the communications. You have a given tile size to make sure the thing is, so this is the size of one tile, and we have more and more larger and larger matrices. And this is the experimental result that we get. So how to read this plot is this is in x-axis you have the matrix size. So we use larger and larger matrices, but also vary the matrix size to look at the effect of communication. And here is the performance expressed in terms of gigaflops per node. And we do this in terms of gigaflops per node because we compare executions where the number of nodes are not exactly the same. And so in orange and purple here at the bottom, you get the 2D block cyclic, the result of the 2D block cyclic distribution with Chameleon. So we have two different cases. We have 30 nodes with 6 per 5 distribution, and 28 nodes with 7 per 4. So that we can compare comparable things. And the symmetric block cyclic for R equals 8 yields 28 nodes. So this is the extended version. And so that's why we have two values. We look at the number of nodes which is close to 28, but which still makes sense for 2D block cyclic. So 30 and 28 make relatively good sense. And they get relatively close performance. And we can see that the SBC distribution achieves significantly higher performance, so like 20% higher or something, because is you perform fewer communications. So we have less synchronization, more time to do parallel computations, and we get a higher performance. So I think this is everything I wanted to say here. At least for the paper, we have in the paper we have more advanced, advanced results in terms of 2.5D distributions and other operations, which I don't need to go into detail, at least not today. This is a good moment if you want to have questions. I'm not sure. I heard several notifications, but I don't think I had anything here. So if you don't have any questions, I can move forward.
I think, Lionel,
now is a good time.
I think, Lionel, now we can look at this curve and maybe say that one expectation, the minimum expectation, is to be able to reproduce a curve that is kind of similar. Is that the case?
Yeah. The goal of the reproducibility challenge is to reproduce this kind of results. So, but I will. Okay. If you don't have questions about the theory and the paper, I can move forward and tell you what we expect from you. So I will change slides. So now this is a slide for the reproducibility challenge. So there's Lionel Erodibois, that's me, Julien Langou, you heard him talk several times, Mathieu Perito. So those three are authors of the paper. And we have also Mathieu Faverge, who is actually in the talk. In the call, you can say hello, Mathieu, maybe.
Hello, I just joined.
So it's perfect. It's a perfectly good time for you to join. So Mathieu is the main developer of Chameleon. That's why he is here for the reproducibility challenge. And Florent Prouveau, who I don't think will join the call, is an engineer in the team who is in charge of maintaining Chameleon also. So he will be helping you with any kind of installation issues. And so the main messages of the paper is that, like, when you change the distribution, you can actually induce fewer communications. And for example, symmetric block cyclic does this. And this results in faster execution. And so this is something we've shown with Chameleon on like 15 to 36 nodes. And so the instruction of the challenge is to reproduce the main findings. It means have something that allows you to observe that actually indeed you perform fewer communications than 2D block cyclic distribution. This is right, something that observe fewer communications and check that actually these fewer communications also results in faster execution on your own hardware, because these results we have had in the paper was for our hardware, which is valid and useful, but maybe your hardware behaves differently, or maybe it will be even stronger, or maybe less. We don't know yet. And so this is the purpose is to reproduce the kind of plot that I gave you at the end of the talk here, that show how fast, how much performance improvement we can get for trilogistic factorization when we change the distribution. So there is a scalability issue here, because most of the teams here have a small amount of nodes, whereas our experiments were done for around like 20, 30 nodes, and it's probably different. SBC starts to show gain, at least in theory, for p equals 6. So probably to observe and to check those results, you wouldn't have to set up several MPI processes per node. Maybe one per GPU or something like this, I don't know. This is something that we will have to, that will be part of your work on identify what are the relevant configurations and how they influence both communications and mostly how they influence running time. Right. So really the goal of the challenge is to reproduce those main findings of the paper, which is fewer communications and how this what effect this has on performance. And so some technical details maybe. So in our experiments in the paper, we use Chameleon and StarPU with some MPI in library and some BLAST. So MKL is what produces the basic what provides the basic linear algebra operations at the scale of one core. So it's no problem. Like, it's actually not a problem that, I mean, using Chameleon and StarPU is not a constraint. You're not forced to. It's fine to use another trilogistic implementation, but it might be challenging to make it use something that is not 2D block cyclic. But if you can do it, why not? In Chameleon, there is support for NVIDIA, there is support for AMD GPUs. And in the latest development version, we have added something for arbitrary custom data distribution. So the experiments we have done in the paper were done with a prototype implementation of SBC, and we have cleaned up this a little bit and made it available for in the main Chameleon branch. So Chameleon is provided in this GitLab repository. All the documentation is available in this link to how to install, but there are very convenient CMake distribution, and if so, Debian and Brew only allow you to install the latest release version of Chameleon. If you want to install the development version, you can either go to GitLab and download it and do it with CMake, or you can use the Geeks and SPAC distributions that allow to compile directly from the development version. everything is explained on this link. I will not describe everything here in the talk, but know that if you have questions, we can help with whatever issues you may have. And Chameleon, more specifically, Chameleon is a C library which provides routines for high performance linear algebra with the goal of providing heterogeneous, and so for GPUs, and distributed, so with MPI versions of those routines. So the main routines are factorizations like LU and Cholesky and QR and others. It supports single and double complex and real arithmetic. It's tested on Linux and Mac on a couple of different architectures. It's interfaced with several runtime systems, but we're mostly interested in the StarPu one because we can easily do distributed versions and GPU versions and custom distribution one. And there is a testing directory with, in addition to the C library, which is you can use in your scientific application, there is a testing directory with executable for each operation and each precision and type of complex arithmetic or not, which is again described in the documentation how to use them. And I have here, for example, the kind of typical result that you will have to get with Chameleon to be able to reproduce our findings. So you start with doing so we do everything with Slurm because MPI and Slurm go well hand in hand. So you allocate your nodes with Slurm. I want 5 nodes and I want 2 MPI processes per node. So this is the kind of Slurm command that you will have that we did for this small experiment. There is a way to ask StarPu to print stats about how many communications it was performed during the run. So this is a good way. This is really useful for this challenge to be able to count how much communications happened during the run. So you just export the variable. And then you do one run. So this is Chameleon testing here is the testing executable that Chameleon offers to test all of the operations. POTRF is the LAPACK name of the Cholesky factorization. This is matrix size, so this is 100K times 100K matrix. This is block size. And this says, okay, by default, this is 2D block cyclic. So this is a parameter of the 2D block cyclic distribution where P equals 5. Since we have 10 nodes, it means it's a 5 by 10, like Q is automatically computed from the number of nodes. So it's a 5 by 2 distribution, which amounts to 10 MPI processes. So this is a command that we give to Chameleon and to MPI exec, and StarPu outputs the total amount of communication that we get. So it's like 20 gigabytes, something like this, 20 million bytes. And the communication time, so it's seconds, so like 42 seconds is how long it took to do the computation. And then you can do the same command where instead of giving the value of P, you say, okay, I have a custom distribution by doing this SBC text distribution, like we describe in the text file, in an external text file. We describe the SBC distribution adapted to this number of nodes. And we can observe that we indeed make fewer communications, so 12 instead of 20, and slightly faster time. So this is the kind of thing that we expect you to be able to reproduce and do a whole set of experiments by varying the number of nodes or the number of processes, the batch size, the matrix size, and so on, so that we can observe the effect it has on your particular hardware. So this is what we expect you to do in the challenge. So the baseline expectation is like you'll be able to install Chameleon or your own Cholesky implementation and experiment with it. Observe that changing the distribution changes the communication and reduces the amount of communication that you do, and quantify the speed up that you get with your particular hardware on this experiment. And you can do more. So I have a list just in the next slide of ideas that you can do to go beyond this baseline expectations. I want to highlight, do not attempt to do everything that I've listed. It will be probably too much. the best thing is do relevant experiments and do them correctly. And I mean, scientifically, in a scientific manner, to be able to observe the things correctly. So the structure of the report, like you should present your architecture because we need to know about how it's organized, and describe which experiments you do, the successful, the failed ones, the relevant ones, and provides results and provide interpretations about how they go. And what you can do is, so as I already mentioned, but I will mention again, that you will have to play with the number of MPI processes per node, how you organize number of MPI processes per node. This changes probably significantly the communications, but you will also need to play probably with process placement to fit the SBC distribution, because to adapt to the topology of your hardware, where you have probably, if you do several MPI processes per node, some MPI processes will have better communications because they will be local to the same node, some other will not. And since the SBC distribution has like specific connections of several nodes, which will be more, which have more communications between them than others, maybe process placement will have a strong impact on the performance. If you have a way, I don't know if there's a way or not, but to measure power consumption of your hardware, if you have this, you can measure energy usage, see if or not whether performing fewer communications results in lower energy usage. It might be useful to hear about this. If you have the opportunity, you can compare the results of Chameleon with other Cholesky implementations like Scalapack or Slate or Elemental or other libraries, see what happens with those. Something which is less of an experiment and more like requires some calculations is do you get the correct amount of communications in your experiment? So compared to what theory predicts, what I showed you in the slides before in the talk, the theory says, okay, you should have this amount of communications, and you get what you should. And something we did in the paper, I didn't present in the slides, is that we went beyond Cholesky factorization. So we looked at what, like, usually after Cholesky, you do, for example, solve. So you factorize the matrix and then you solve for a particular value of x, a particular value of b, sorry. So factorize plus solve, the two in sequence, and see if we can still observe fewer communications. And so 1 and 2 means fewer communications and change in performance for the solve, and POTRI is the Cholesky inversion, where you start with Cholesky factorization and then you do several sort steps to get the inverse of the matrix. There is in the paper also did 2.5D algorithms, but this requires a higher number of nodes or processes, so maybe it's not relevant depending on your hardware. Maybe it is, maybe it is not. Since after this SC paper, we got 2 papers accepted to IPDPS of 2023, whose links are given here, which explore other possible distributions than SBC, still for symmetric or for non-symmetric cases. You might want to try those if it helps or not. And there are probably many other possibilities. It's, I mean, we are very open to you being creative and curious about these questions. And I'm done with my talk. If you need more information, you're free to contact us. Now is a good time to ask questions. Later will also be possible. We will be present on the discourse server. Of course, we might not answer immediately. So the sooner you ask the questions, the more we can provide information and help. We are mostly on French time, all of us, except Julien, who is in Denver. So this might help you know if and how we will be able to answer. So that's all I have to say for today, and I'm very happy for you to be here and to participate, and I'll be delighted to answer your questions if you have any.
I'll ask a question. So You use
Yeah.
the MKL libraries out of Intel. Is that correct? Right? If I remember
Yes,
that
we use Intel.
previous slide.
In our experiment, we used Intel MKL, but it's not necessary, and so maybe I can.
Sorry, Lionel. You can use any sequential BLAS library. What is important is to configure it to use it as sequential because we take care ourselves of the parallelism. If you use multi-threaded BLAS library, they may conflict with each other because you have multiple concurrent cores that are done. And so the performance may slow down because of that. So you can use any BLAS library, you just have to be careful to set it as a sequential library.
And in particular, Chameleon is compatible with QBLAS and HipBLAS if you want to use GPUs.
Great, thank you. I don't see any other questions. We don't have a ton of students here, which is fine. We're recording this, so they'll all be able to watch this later. But I don't see any other questions from the students. I don't see any questions in the chat. But that was really great. I appreciated that. I followed that pretty well. It's really interesting, actually. I'm curious. I'll be curious to see what the students do with this. So, yeah, it's pretty slick. Yeah. Some nice linear algebra in there too, which is great. So this is a nice challenge.
Hey, good morning. I just was going to ask if you posted those 2 papers in your talk, and I know, Jeanette, you guys are doing a great job getting the webinars up very, very quickly, and 7 a.m. for my team is a bit early, so they'll be watching that soon, and Kai is here, who's our team lead for the app. But do you think you could put those in the chat so we could, oh, I see them, get them in the
Yes,
papers? I'd appreciate
so
that.
yes, I definitely can copy paste. I can copy paste that in the chat, but I will definitely have the slides up in the somewhere on in the website of the challenge.
Yeah, I know that they're getting them up.
So the slide.
Yeah, great. Thank you. I'll pass those on to the team.
Yeah, we'll get these on get the slides up with the webinar recording, so you'll be able to find these in the slides. Okay, Mary?
Yeah, Jeanette, my compliments to you on how quickly you guys are getting them up. I noticed that they're up already on the Student Cluster Competition US site. So
yeah, at least the first 2. I'm having a hard time getting the 3rd recording from Doug, but once I get that, I'll get that up, and we'll get this up fairly shortly.
Okay.
So.
Thank you. Yeah, this looks like a fun app. Some basic computational methods and approaches. So, like you said, some basic linear algebra. I'll relearn some. Okay.
Well, and it's not too complicated, right? We're just talking about the transpose. So some real basic linear algebra, right? We're not doing anything too fancy. And it's
Right.
lovely. Yeah.
Okay, thank you.
Hi everyone. I might have a question regarding the tile sizes of all the things, because in paper we've also mentioned that you've tested on different tile sizes to suit the hardware. So I'm thinking if you have any recommendations about the tile size that we can try on our own hardwares.
So there's a very important difference in terms of tile size depending on when you have GPUs or not GPUs. Usually, the way we configure our star PU in most of our experiments is to use only one stream. So when you use only one stream, like there's only one computation going on the GPU at a time, this helps star PU make sure that the running times are stable, like executing one operation takes always the same time. But then if you want to use the GPU efficiently, you need large tile sizes when you do only one computation at a time on the GPU. So if you use GPUs, I suggest you use larger tile sizes. But other than this, like on our GPUs, we usually use 2,000 or 3,000 or 4,000 tile sizes on our GPUs when we do runs. Mathieu, if you want to prove me wrong,
So
you're welcome.
if I can add something, I think so. First of all, you could start with the tile sizes that are used in the paper. So it's for CPUs only, for sure. So you can just increase a little bit depending on the GPU you are using, the 100, A100, or AMD GPUs. You may increase it a lot or not to get good performances. But I think that the most important here to reproduce is to assess the communication volume and the changes of the different strategies. So basically, what will be the most important is to take the same tile size for the two configuration, 2D block cyclic and SBC. And you should observe more or less the same effect, whatever the tile size you are using. As long as you use the tile size, it is in the correct range for the GPU, which is quite large. You should have the same effect, whatever the tile size you are using. So it should be fine. It's not a big deal if you don't use the correct one.
Okay, thank you.
And the trade-off about tile size, is if it's too small, that the GPU is very inefficient, and if it's too large, you have not much parallelism to go with because you have you have very few iterations and you have not much parallelism. So there's a trade-off here, but as Mathieu said, the range is quite large.
Yeah, and one of the things also is that in the current version of Chameleon, you won't have the factorization kernel made on the GPU. So if you go too large, you will be slowed down by the critical path. So, I mean, you have multiple criteria here. Is that larger is the tile size, less tasks you have, so less parallelism. More efficient you are on the GPU, but you still have this factorization kernel on the diagonal that will slow you down if you make it too large. So that may be a problem. And in the end, this is, as I said, it is not the phenomenon you want to observe here. This is two different criteria, two orthogonal criteria, I would say, to optimize your code on multi-node architectures. So one is to try to optimize the number of communications. The other is to have the perfect tile size to get the most out of each computational unit. If you don't get the second one perfectly, I don't think it matters a lot, unless you want to compare to the best library it exists.
And another question is, while we were trying to those operations that beyond the factorization, for example, the POTRI, which is including both the factorization and the solving problem among
and the inversion.
Yeah.
POTRI is with the inversion.
Yeah, and among them, some of them are not symmetric, and which is also mentioned in the paper. Like, while as an extension, shall we just try as a whole using the same data distribution, or following the paper doing different distribution for different operations?
So I would say that for POTRIs, you are using only the matrix that you factorize, and you do all computation in place. So you will use only the SBC distribution. For the solve, I will let Lionel answer, because I don't know how they did the distribution for the right-hand side matrix. I don't remember it.
So actually, in the paper for the POTRI, we actually did something that was change the distribution in the middle of the execution. Because indeed there's a non-symmetric operation in the middle, and so this requires like doing this will require. I mean, if you want to do it, it's fine. You're very welcome to test it and see what happens there. it's more involved or challenging because you will need to like dig into the code of the testing executable that does this to actually change by hand. I mean, not by hand, but to include the code that makes the change between from one to another. It's not very. It's not a lot of work, but you really need to understand how to use the Chameleon commands to change those. But already testing with SBC from start to finish is also interesting. I do not remember the theoretical results which say how much communication gain you get when you do this. But it's also, I mean, right, as I told you, any relevant and experiment which is done correctly is interesting for us to analyze and for you to look at.
I see. Thank you for answering. Maybe I will try if I have extra time.
Yeah. Okay, perfect. So something I wanted to say, I will also give you the link. It's not in the slide, but I will give it to you. I can give you access to the code that we use to make the experiments that we did in the paper. But this code was using a like prototype version of the code for SBC, which is not the same as the one we developed in the main branch of Chameleon for now. So it's probably much better to use some of this will be used. You can use this as an example of what exactly we did and how it can be done, but probably will need to be re-implemented on top of the latest Chameleon for now. So it's probably not a good idea to reuse the code as is, but it can be a good inspiration of what it is you should do. Thank you very much for the questions. Anyway, they're very good questions.
I don't see any more questions. We're coming at an hour, so yeah. Thank you so much for your presentation. Do you want to give me back the host? And
okay,
stop
sure.
sharing
If
here.
I find out how to do this, I'm not sure I know how to do that.
Oh, I can reclaim it. I'm going to reclaim it. Here we go.
Okay.
Excellent. I'm the host.
Go ahead and do that. Yes.
Great. All right. And then I will stop this recording. So thank you so much to the reproducibility team for this great webinar. Webinars have been really good. I really appreciate y'all doing this. It's really helpful to the students. And so thank you so much. And I will stop this recording.
Thank you, Jeanette.